All right, let's get into it. Today we are tackling a classic physics problem from Irodov, one that really makes you stop and think about something we take for granted: energy. It almost seems like it bends the rules of reality, but as we'll see, it's all about your point of view. So this is the big question, right? How on earth can one system have two totally different energies at the very same moment? It sounds impossible, but trust me, it's not a magic trick. The answer is all about perspective. In physics, we call it your frame of reference, and it is absolutely the key to solving this whole puzzle.
And here it is, the problem itself. I know, reading it straight like that, it can sound, well, a little dense. It's packed with physics jargon, but don't let it intimidate you. We are going to unpack every single phrase piece by piece until this whole thing makes perfect sense. I promise.
So here's our roadmap. We'll start by defining the two different points of view in the problem. Then, we're going to break down exactly where the energy comes from in each of those views. After that, we'll build the mathematical bridge that connects them. And finally, we'll put it all together to get our answer. Let's jump in. Okay, first things first. Let's tackle the most important concept in this entire problem. We are not looking at two different systems. It's just one system, but we're looking at it from two completely different viewpoints. Or, as a physicist would say, from two different reference frames.
So first up, we've got frame K. The easiest way to think about this is as our stationary lab frame. Just imagine you're standing still on the ground, watching a spinning asteroid fly past you in the sky. You see the whole thing, the asteroid, moving from one point to another. That viewpoint? That's frame K.
Now, for the C frame, the problem calls it the center of inertia frame, which, for what we're doing here, is the same thing as the center of mass frame. So to get this, imagine you're now a tiny camera that's been bolted right onto the center of that asteroid. From your new perspective, the asteroid isn't flying across the sky anymore, is it? Nope, you're moving with it. All you can see is the rock spinning and tumbling around you. That's the C frame.
Okay, so let's just put this all side by side. From the stationary lab frame, frame K, you see the whole system moving by with velocity v, and you measure its total energy to be E. But if you're in the moving C frame, the system's center looks like it's at rest. The only energy you measure is all that internal tumbling and spinning, which the problem calls E tilde. That little squiggle, the tilde, is super common in physics. It's often shorthand for a quantity that's measured in a different, usually moving, frame.
All right, so if the energy value is different in these two frames, you have to ask yourself, where's that difference coming from? What's the deal? The secret is realizing that the total energy you see in the lab frame is actually made of two totally separate parts.
Let's really think about this for a sec. The observer standing still in the lab frame sees everything that the camera on the asteroid sees. But they see something else too. What is that extra piece? Well, it's the motion of the entire system as one big object. And this is the core idea right here. From the lab frame, you see the external energy. That's the energy of the whole system just moving through space. And you also account for the internal energy, all the spinning and vibrating of the individual parts. The C frame, on the other hand, only sees that internal part.
So this is it. This is the key insight. The total energy that an outside observer sees, which we call E, is just the sum of two things: the energy of the system's overall movement, plus all the energy that's going on inside it. This single idea is the conceptual breakthrough that cracks the whole problem wide open.
Okay, the concept is down. We get it. Now it's time to translate that physical idea into the language of math. We're going to build the formula that acts as a bridge, connecting our two different energy values, E and E tilde.
We're just going to start with that simple word equation we just figured out. This is our foundation. All we need to do now is swap out the words for the actual symbols the problem gave us.
Let's connect the dots here. Step 1 is the easy part. The problem literally tells us that the total energy inside the C frame is just E tilde. Done. For step 2, we have to describe the energy of the system's bulk motion. And that's just the good old-fashioned kinetic energy of a single object.
And here she is, the beautiful, fundamental formula for kinetic energy. I'm sure you have seen this thing 1,000 times. 1/2 mv squared. It's the classic equation for the energy an object has just because it's moving.
So we just apply that formula to our system. The problem says the system has a total mass m, and from the lab frame's point of view, it's moving with a velocity v. So its bulk kinetic energy is, you guessed it, 1/2 mv squared.
And now for the final step. We just plug our two mathematical pieces back into our word equation. The total energy, E, is the energy from the bulk motion, that's 1/2 mv squared, plus the energy inside the system, E tilde. And that's it. That's our formula.
And just like that, we've done it. We built the formula from scratch, just using physical intuition, and we successfully bridged the gap between the two different reference frames. So let's go ahead and state our final answer clearly.
Now, just so you know we're on solid ground, our logic is actually backed up by a very important principle in mechanics called Koenig's theorem. It basically confirms what we figured out. The total energy is the sum of the external and internal kinetic energies. And our E tilde also includes any internal potential energy, which, by the way, doesn't change when you switch between frames moving at a constant velocity. So our logic holds up perfectly.
So here it is, the solution to the puzzle. The total energy in the lab frame, E, is equal to the internal energy, E tilde, plus the kinetic energy of the entire system's motion, 1/2 mv squared. It's such a simple and really powerful result.
So, what are the big takeaways here? First, energy is relative. Its value really does depend on your frame of reference. Second, the stationary observer always measures more energy because you have to add in the kinetic energy of the system's bulk motion. A super common mistake is to forget that bulk energy term. But now you know exactly where that so-called extra energy comes from.
And that brings us to a final thought. We've just seen how this powerful idea of separating internal and external properties works for energy. But you know, energy is just one of the big concepts in mechanics. How would the same way of thinking, comparing the lab frame to the center of mass frame, apply to another crucial quantity, say momentum? Now that's a great question to think about.